lecture on machines, and in our last class we defined sleep as sleep is equal to S is equal to Ns minus Nr by Ns, and Nr of course may change, but Ns is fixed, which is in mechanical RPS 2 F by P. P is the number of poles of the machine, and the value of sleep can be between 0 to 1. S equal to 1 corresponds to locked rotor condition. Whenever rotor is not moving, you have energized the primary. Of course, rotor circuit is closed, then that is sleep equal to 1, and extreme case sleep could be equal to 0, provided there is no opposing forces, no opposing torque, which is of course is not a very ideal situation. And also we discussed that if the machine is having some under no load condition, but friction cannot be avoided. So, machine under no load condition means only opposing torque whichever is present is very little and may be due to friction. When we say that the machine is loaded, means we are increasing that opposing torque, and in our last class I discussed how machine will settle down to a final speed after you have started it from S equal to 1, S decreases and so on. And also the same expression is very useful to write in this way. Ns is constant. So, instead of telling speed directly, people would love to tell sleep of the induction motor at which it is operating. From that, of course, I can work out what is the value of speed. So, this is another thing. And then the important thing we told you is that the stator induced voltage E 1 was equal to root 2 pi f phi into k w 1 n 1, and at any value of sleep E 2, at any value of sleep, the induced voltage will be root 2 pi S f into phi into k w 2 into n 2, where S f is the frequency of electrical quantities in the rotor, frequency of V I in the rotor circuit. Now, this is equal to S into root 2 pi f phi k w 2 n 2, and at S equal to 1. So, this is S, and this quantity is nothing but the induced voltage E 2 at S equal to 1, called the E 2 at S equal to 1 is called the induced voltage per phase in the rotor coils when the rotor is at standstill condition. So, that is the thing. Achha. Now, in today's class, what we would like to do? We will try to draw the equivalent circuit of the induction motor per phase equivalent circuit. Now, it looks like, suppose rotor is stationary, then in the stator I have applied a voltage. Suppose V 1 is the per phase voltage applied and also note that E 1 by E 2 at S equal to 1, E 1 by E 2 is equal to 1 is nothing but k w 1 n 1 by k w 2 n 2, and this can be termed as a turns ratio between stator and rotor, effective turns ratio. Now, what happens is this, I will not first tell like this, then let us try to understand. So, at S equal to 1, I know the induced voltage in the rotor circuit is E 2 at S equal to 1, and the frequency of the rotor current is also F. So, at S equal to 1, F r is equal to F, because S into F, S equal to 1. Standstill condition means at S equal to 1. Therefore, it looks like at S equal to 1 at least, this is just like a transformer, because you have energized the primary with a 50 hertz source and the rotors are shorted, yet to start. At S equal to 1, you have applied some voltage, frequency is F, here also it is F, and this voltage, induced voltage E 1 and this is E 2 at S equal to 1. This ratio is a constant, stator turns is to rotor turns, and also the frequency is same. So, it is just like a transformer, at least at S equal to 1. If you can maintain that condition S equal to 1, okay, it will never run as a motor, but will behave like a transformer, because transformer what it does, it changes one given voltage to another level of voltage without changing the frequency. Frequency remains same on both primary and secondary. So, at least at S equal to 1, therefore, it looks like the equivalent circuit will be just like a transformer. That is, there will be a stator, if it is not an ideal winding, of course, per phase resistance is R 1, there will be leakage reactance, this winding is having R 1 and X 1. So, there will be a leakage reactance X 1, then there will be a magnetizing inductance X m. Why not X m? I will write capital because X m is much higher, and that is all. That is, and here is your E 1. Is not in transformer also applied voltage and E 1. If R 1 X 1 you neglect, V 1 is equal to E 1. Mind you, R 1 X 1 are small and X m is large, many times larger than R 1 X 1, like transformer. In fact, compared to a transformer, the magnetizing reactance of an induction motor is much higher, because of the fact that there exists an air gap, and to establish a same amount of flux in a transformer or in an induction motor, current needed will be much higher, that is the magnetizing current. Therefore, X m is much higher current is necessary. So, to establish a given flux, and then here is your E 1, here is your E 1, and secondary side what happens is simply this one, this is the secondary coil, secondary circuit is closed. So, per phase the induced voltage at S equal to 1 will be E 2 at S equal to 1, and the circuit is closed. Therefore, it will have the winding, this R 2 is winding resistance, and it will have a leakage reactance X 2, and this is the winding thing, and this is shorted, this is shorted. This will be the equivalent circuit of the transformer at S equal to 1. The frequency of E 2 is F, and frequency of any current here is also F. Therefore, it is just like a transformer. The supply voltage is of frequency f. After subtracting the drops, small drops in R 1 X 1, whatever voltage is available, that will be the magnetizing reactance and so on, and this is R 2 X 2. So, these are source of EMF in case of transformer equivalent circuit. From the circuit point of view, we derived at the very first or second lectures. Therefore, and this is the X 2 here. What is X 2? X 2 is the leakage reactance. So, let me write R 1 is equal to per phase, all per phase stator resistance, X 1 is equal to per phase stator leakage reactance, stator leakage reactance. R 2 is the per phase, no point in writing per phase rotor resistance in ohm obviously, and X 2 is the rotor leakage reactance per phase. Now, reactance, you see this reactance should be further qualified. Why? Because of the fact that this is at S equal to 1, this is fine. So, any reactance is 2 pi f into L inductance, that is omega into L, omega is 2 pi f. Therefore, in whichever circuit that L is present, its reactance omega L depends upon the frequency. In case of a given supply, to analyze circuit, frequency is fixed everywhere. Therefore, you can that x value whatever you are showing in the circuit, that is omega into L, omega is fixed. Now, here is a different situation in case of induction motor rotor coil. Why? Because at slip S equal to 1, frequency in this rotor phase will be f equal to the supply frequency. But when the motor will be running, the frequency of the rotor electrical quantities will be S into f, that we know already. Therefore, resistance of course will not change because of that change in frequency in this closed circuit. However, the reactance value is then is to be modified, is not. So, what we say is this X 2 is the rotor leakage reactance when rotor is stationary. Or rotor leakage reactance at standstill condition. Rotor is standstill condition. So, this must be remembered, and this is this equivalent circuit at S equal to 1. Now, in this case, therefore, I will say that okay, from circuit analysis or whatever it is, I can then connect these 2 points with these 2 points, provided I do this R 1. Let us do it on a other page. So, at S equal to 1, at S equal to 1, only thing I will write that stator frequency and rotor frequency are same. Rotor frequency are same. Therefore, it is just like a transformer. Because E1 by E2 is equal to Kw1 by N1 and Kw2 by N2 effective turns ratio, and equivalent circuit referred to stator will be simply this. This is S equal to 1 standstill condition. This will be the equivalent circuit provided you have multiplied this with a square, where A is this, that is the turns ratio of primary and secondary. This is X m and this is V 1, absolutely fine. So, this is equivalent circuit referred to stator. Now, the question is, what will be the equivalent circuit? Circuit is what? When motor is running with some slip, slip S, which is not equal to 1. Under that condition, if I draw the primary and secondary coil separately, it will be like this. V 1 is the applied voltage per phase on the stator windings. This is R 1, leakage resistance and leakage reactance of the stator, and this is your JXM, is not, and here is your, I mean that coil which is having a voltage E 1, and all frequencies here are F. And on the secondary side, there is a source of EMF, or just a coil I will draw, and here is R 2, here is the reactance, and it is shorted. But the frequency of the rotor electrical quantity is SF, which will be less than your supply frequency, because S is a number which is between 0 to 1. It is going to be less. For example, if the supply frequency is 50 hertz and motor is running at a 5% slip, the frequency of the rotor current will be 0.05 into 50, that is 2.5 hertz. Okay. Low frequency compared to this 50 hertz. Now, in this circuit, therefore, frequency of primary and secondary coil are different, that is one thing. And second thing, another modification I have to do, because the rotor current or voltage frequency is SF. Therefore, this reactance X 2 was at 50 hertz. Therefore, what will be its reactance as SF hertz? At F hertz, this reactance was X 2, at SF it will be S into X 2. Obviously, 2 pi SF into L. If L is the leakage reactance, you can easily show. So, this should be S. and that is it, and this is of course your E 2, E 2 at some s, which will be also less in terms of that. So, this is the scenario at s equal to 1. Now, the moot point is these 2 points, can I am slightly in a difficult position now, in the sense okay, there is a primary coil, there is a secondary coil, the ratio of the volt and this voltage A C 2, it can be also written as S into E 2, where E 2 is the voltage at standstill condition. Okay. If E 2 is the voltage at standstill condition, then the induced voltage when the motor is running with slip S must be S into E 2, that we have seen. So, mind you, this E 2 is the voltage at standstill condition. So, this is the thing. Now, see here also see E 1 by E 2, this voltage by this voltage is no longer simply a turns ratio, there is a S factor coming in. So, also the about the current, the frequency of that current and voltage is S f, and it is so frequency of this is S f, and this voltage E 2 S secondary voltage by primary voltage is no longer a constant A. So, at least I know this much, it will be a mistake if I just multiply this with a square and connect it here. Okay. This will not do, because the frequency at least must be same and ratio of the voltages must be properly defined. Now, how to overcome this situation? Achha. Suppose the motor is operating at a slip S and the rotor current is I 2 suppose, and this current will be at frequency FR, SF. Achha, what is the RMS value of this rotor current? RMS value of the rotor current will be E 2 S A C 2 divided by square root of R 2 square plus reactance square. X 2 is the reactance at standstill condition. So, that is why the reactance has modified. This is the expression of I 2. Okay, fine. Now, this I 2 is equal to A C 2 divided by square root of impedance, that is R 2 square plus S square X 2 square. Okay. And this is the RMS value of the current, RMS value obviously, actual rotor current. So, rotor circuit was like this, there was a voltage source A C 2 and it is R 2 and this is S into X 2 and this current I am talking about. Frequency here is S f. Achha. Now, let us see this expression of the current, I will manipulate it a bit. In which way I will manipulate? I will divide both numerator and denominator by S. So, that this will become E 2 divided by square root of this is R 2 by S whole square plus X 2 square. This way I can write it. That is, I am dividing this circuit I am trying to draw it like this. Okay, there is E2 and this resistance you divide by S, it is R2 by S, and this reactance you divide by S, you get X2 and you close this. These two circuits, so far as magnitude of current is concerned, RMS value of the current, it will remain same, this circuit and this circuit, is not the magnitude of the current is to remain same. Now, a little bit of talking. See what happens in a transformer. In a transformer, this you listen carefully. Suppose in a transformer, secondary is open circuited and primary is energized with a voltage V1. Then what happens? It draws only the magnetizing current, because that second part of the circuit will be absent, because it is open circuited, no Z2 is connected, and that is called the magnetizing current and Xm. Now, this point is important. Now, when you try to draw some current out of the transformer, this is the physical reasoning I am trying to tell. The moment you want to draw current from the secondary of the transformer by connecting an impedance, on the primary side, no matter what you do on the secondary side, do you think the flux in the core of the transformer is going to change? Practically, there will be no change in the flux which was present when this switch was opened or when this switch is closed. The flux in the core of the transformer, that cannot change. Why that cannot change? Because the supply voltage, the KVL is to be satisfied here in this winding. Applied voltage small r1 x1, which suppose you neglect. So the EMF here gets fixed by this V1, nothing doing. No matter whatever you are doing on the secondary side, you are shorting, you are closing, some resistance, some inductance, do whatever you like, the net flux in the core will not change. That is why people say MMF balance, N2 I2 is equal to N1 I1, reflected current. So, the moment you close it, but how it can manage to do that? Under no load condition, it was drawing only the magnetizing current to establish the flux. The moment you close the switch, I am sure there will be a secondary current. Therefore, the extra MMF which is now brought into this system, because you have connected a load on the secondary side, primary cannot but draw additional current called reflected current, apart from the magnetizing current, whatever it was drawing. And the value of this I2 dash will be such that N2 I2 is equal to N1 I1. It is in relation to a transformer, I am telling. N2 I2 is equal to N1 I2 dash, extra current it will draw in apart from this IM, such that N1 I2 dash is equal to N2 I2. Look at the dot convention, their MMFs will be always cancelled out. Therefore, flux in the core will remain only due to N1 into IM, the magnetizing current. Is not, that is what it will do. That is, in other words, what I am telling, if you have a unloaded secondary of a transformer open circuited, current drawn by the transformer primary is magnetizing current. If you close the secondary coil with some impedance, that is, want to draw some current out of the secondary, primary cannot remain a silent spectator to this. It will immediately react by drawing extra current I 2 dashed, such that N 1 I 2 dashed is balanced by N 2 I 2, and these two MMFs will be in opposite direction. From the dot it delivers, from the dot it takes current, such that the total MMF existing in this circuit is once again N 1 into I m, the magnetizing current, and flux remain constant, and everything is now nicely satisfied. That is, KVL is satisfied, flux has not changed, and your MMF balance also takes place. Any extra current you draw, things will be that. Now, coming this way to the induction motor, see, induction motor, it is like this, and suppose this switch is open circuited initially. See, mathematics is very simple, but try to understand what I am telling. It will give you some interest, it will help you to grow some interest about this machine. Now, here suppose this switch is open, induction motor, this is right, this was transformer. So, 3-phase induction motor, you have energized the primary 3-phase voltage and you have closed it. The moment you close it, a rotating field results, there will be induced voltage, and there is some flux per pole. And here also this R 1 X 1 of the stator primary, if you neglect, the flux which will be produced is root 2, which is approximately equal to root 2 pi f phi k w 1 n 1. So, from this equation we will continue next time. Thank you.